Hello everyone, you are welcome to the third episode of our structural analysis of a filling station, where we are attempting to have a structural design of base plates and bolt connection for the base of the column. In the first episode we did the overview of whatever we want to do, and then we also did the loading analysis. So in the second episode we did the structural analysis, where we calculated the axial force at the base of the column, we calculated the shear force at the base of the column, and we calculated the moment at the base of the column. So in this third episode we will be having the structural design of the base plate. So when we say we want to design a base plate, what does that actually mean? What are we designing in base plates? So we are only designing two things in base plates. Let me change the ink. So the first thing we are designing is we are designing the area of base plate, and second thing we are designing the thickness of base plates, and that is all. These are just the two things we want to have. You can't just say, okay, let the surface area be 200 by 200 and use a thickness of 5 mm. Okay, no, you can't just say that. You have to show us the structural calculation so that we can know that this is enough. Because if the base plate is not adequate, then there's no how the axial force coming from the column will be distributed. If you have axial force, you need to first of all distribute it over an area, right? So if that area is not wide enough, then you are not doing anything. Okay, so that is what we mean by base plate design. We are trying to get the adequate area, and then we are also trying to get the adequate thickness. Okay, so the first step in doing this analysis is that we need to know the pressure, the bearing pressure of the base plate. So basically, when you have a base plate, let me have a kind of elevation. So this is my plinth, which is concrete plinth, right? And then you have your base plate on it. Okay, so you have base plate, and on this base plate we have the UC beam, right? UC beam, and then this UC beam most times will be welded to the base plate, so that's the connection between that. And then the base plate will now have to be connected to the column using anchor bolts, right? Anchor bolts, right? Okay, so the two things we are trying to design here, we are trying to design the base plate and we are trying to design the anchor bolts. Okay, so that is the scope of this structural analysis. So now if you see this, you see that the base plate is actually sitting on the concrete, right? The base plate is sitting on the concrete. So the bearing pressure, which is definitely the pressure at the base of the base plate. So if this is the base plate, we're expecting that there's a pressure under it, right? Okay, and that pressure is as a function of the kind of material it is supported on. So if it is supported on a concrete plinth, you are expecting a particular kind of pressure. If it is supported on a masonry, you are expecting a kind of pressure. If it's supported on a mortar, you are expecting a kind of pressure. So we have to know what the bearing pressure under the base is. So I would just say the bearing strength of concrete, the bearing strength of concrete plinths, the concrete plinth is what is supporting the base plate. So that is equivalent to 0.6 FCU. You can check the Euro code for that, and we have said it, our FCU is 30 Newton per millimeter squared. So now I want to calculate the area of the base plate, and in order for me to calculate the area of the base plate, I first of all need to know what the effective area of the base plate is, because it is the effective area of the base plate that will give me an idea of what the area is. Okay, So what do I mean by effective area? So this is what it means when you have a UC beam. Obviously it is a UC column that is connected to the base plate, right? So I will just have like a plan view. So if you have the UC column like this, that UC column that is connected to the base plate, what I'm saying is that the effective area of this is something around like this. Okay, so the effective area of the base plate is expected to take the shape of the element that is attached to it, because that element that is applying the pressure. Okay, so if this is our UC beam, as I said, from a position up to here, which is called C, I know that the pressure coming from this base plate will not pass a particular distance upward here, and that particular distance is called C. Also, from the side here, you know that okay, the exact thing it will apply here is like C. Also from here to here, C. Okay, so we can say that the distance from here to here, we can call that 2C plus small t. I already said that from the edge of this column to this position is C. Also from this position is C. I know that the thickness, which is the web thickness of this flange, is called T, right? So this is C plus C plus T. So that is 2C plus T. All right, good. So the distance from here to here is C. All right, the distance from here to here will be 2C plus big T, right? Because from here to here is C, also from here to here is C, and also this is big T, because the thickness of the flange is called big T. What I'm saying is that when you have your UC beam, okay, so around here you are expecting that the pressure this will exert on the base plate is somewhere around like this. It will take the shape, right? All this shaded area. So all this shaded area is the effective area. So since you know that this is the effective area that the pressure of this base plate will be having, so you are not expected to have your base plate anywhere in this shaded area. So your base plate cannot be like this. If the area you are providing for your base plate falls inside this effective area, then it has failed, because the pressure exerted on the base plate from the UC beam is actually spreaded over an area wider than this. So this has failed. Do you understand that? So the area you are meant to provide has to be equivalent to this effective area or more than effective area. Definitely it has to be more than. So the area you'll be providing must not fall inside that effective area. It has to fall outside. So you can have like an area like this for your base plate. Oh goodness, see what I'm sketching. Okay, so if you have this kind of area, then it passes, because that area is outside the effective area. That area, the pressure coming from the UC beam cannot go beyond it. The pressure of the UC beam is within it, so that is fine. You understand? So our first attempt to do now is that we need to calculate what this effective area is. So the moment you know the effective area, then from there you can calculate your required area, or the area you want to provide. Okay, and as I've said, to know your effective area is quite easy. If this is your UC beam, you just need to know that from the edge of your UC beam to the position where the effective area terminates, you can call that C. Okay, so at every end C, so to the top C, to the side C, to each side C. Okay, so that's why I'm not trying to say that, okay, from here to here, that will definitely be 2C plus T, and also from here to here, that will definitely be 2C plus T, because from the edge of your UC beam to the end of your effective area is C, here C. So this is the thickness of the flange. Thickness of the flange is big T, right? So you just need to do a small mathematics, and then you can easily calculate this total area. You know, it's like an irregular area. Okay, so you just need to maybe derive your formula from it. Okay, if this side is C, this side is C, this side is 2C plus T, this side is 2C plus T, then you can just derive your equation from that. So I'm not just going to waste too much of time in trying to derive the formula of this particular section. I have done that, so I will just write it out. Then it's left to you to go and confirm if I've made mistake in the derivative or not, but definitely I've checked through it properly. So as I've said earlier, we need to know the pressure under the base, and the pressure is actually is 0.6 FCU. This is the formula for the pressure, is 0.6 FCU. So we can easily say that effective area is equivalent to what? Axial load from the column to the base plate. Let me just say axial load on base plate. But when I say axial load on base plate, you know where it is coming from. It is coming from the column, and the load on the column is coming from the beam, and that is coming from the canopy. So it's equal to axial load on base plate divided by what? Divided by pressure under the base plate, which is the bearing strength of concrete, right? Bearing strength of concrete, or you can say concrete, or you can say pressure under the base plate. Okay, so what is the axial load? That is 83.01. Let me see, 83.04, sorry. So that is 83.04. that's in kilonewton. So I'll kind of want to multiply that by 1000 in order to convert to Newton. Don't forget that your bearing strength is in Newton per millimeter square, so I have to convert this to Newton too. So that's why I multiply by 1000. And what's our bearing strength? I already said it, that it is 0.6 FCU. And what's our FCU? 30. Sorry, I'm just realizing that in the calculation that I have here, the FCU I use is 15. Okay, so I don't want to change that, because that will be I will have to be pressing my calculator one more time, which I don't want to do. So I'll just change this back to 15. So I'll change this to 15. Okay, because I want to be picking the value from what I've calculated. So from there, my effective area will now be equivalent to 9226.7 millimeter squared. Okay, so this is my effective area. So this is what we just calculated. All this shaded area that I have here is all the shaded area in red. That is the total area. Okay, effective area. So that is good. However, don't forget that we need to know the value of this C. Just as I've mentioned, since I told you that from this position to this position is C, this position to C, this is 2C plus T. So you can just easily calculate, you can just have your kind of equation to get that. Let's say for example, you can say that, okay, fine, if this from here, from here to here is B, right? From here to here is big D, right? Okay, so you can easily know that from here to here will be B plus 2C. Do you get that? And also from here to here will be D plus 2C. So you can just try to close this down, close this small portion down, and then have this. So this side is nothing but 2c plus t. So you can have three areas like this, right? So you have tried to solve it like this. Know that okay, here what you have there is 2c plus t, and here what you have here is b plus 2c. So you can get the area of this place like that, because this is a rectangle, so that's length times breadth. So b plus 2c times 2c plus t, you have the same thing here as well, right? So what is going to be the height of this? The height of this is just going to be if the total length of this place is called d plus 2c, then this place will just be d plus 2c, right, minus 2c plus t, right? That will be the height. And what will be the width? The width is what I already said here, that the width will be 2c plus small t. So it's now left to you to calculate the area here, calculate the area here, calculate the area here, and add it up. Okay, so you just need to do that small mathematics. That is what I'm trying to say, that you derive the equation here. So I would not go into that, but I think I've explained how you are going to get that. So I will just write out what I have derived. So my effective area, I'll call it A effective, equals to 4c square plus 4 b plus t, big T, okay, minus 2 t minus small d, everything multiplied by c, plus 2bt plus td. Okay, so this is what I derived eventually after using something like this. So if you check textbooks, you might see that maybe the way they even write this formula is quite different, but at the end of the day it is still the same thing, because I have tried to put it in some bracket and all. Maybe they expanded the bracket and do it anyhow. So it's all, you just need to derive that. Okay, so and the easy thing is that even all of this like this from here to here is basically the column perimeter. Yeah, and all of this here is nothing but the column area. What I mean, the UC column. Okay, that's UC column area. This small equation, you can call it maybe equation 1. Okay, so I've already calculated what the effective area is, which is this. Okay, I've calculated what the effective area is. Now we know what B is, we know what T is, we know what small t is, we know what small d is, we know everything. The only thing we don't know is C. Okay, what's our B? Don't forget our B is 203. Don't forget that the section is 203 by 203 by 46, right? So you can just check your blue book so that you can get the property, the steel property, or you can check online. Okay, so let's check it up online. I'll just say UC properties, UC column section, and let me this. Okay, so let's use this Renam steel. Okay, so let's look for our section. Our section is 203 by 203 by 46. This is our section, right? Okay, so if you check, your mass per meter is 46.1. So 46.1 and 46 is actually the same thing. So, and your depth of section, which is your big D, is 203.2. Okay, 203.2, and your big B is what? 203.6. Your small t, which is thickness of web, is 7.2. Your thickness, which is big T, is 11. Okay, and then I think that's all we need this case. So I'll just take it with this. I just showed you so that you can easily get this from your blue book as well. So you can check blue book or you can just check online, whichever one is quite easy for you. So I think my B is 203.2. okay, and the big D is 203.6, just as we checked right now. My big T is 11, which is the thickness of the flange, and then my small t, which is the thickness of the web, is that's 7.2, and then my small d, 181 millimeter. Okay, small d is equal to big D minus 2t. Yeah, minus 2t. So now all I need to do is that I just need to put all of this value into here. Okay, you already know what your effective area is. Your effective area, this is the value, right? What is B? This is B, right? This is B, this is the value for B. What is T? This is the value for T. What is small t? This is the value for small t. What is small d? This is the value for small d. Big T is here, so the big T. So you just go about that. The only thing you don't know here is C. So at the end of the day, when you put all of this together, I'm expecting you to have 9226.7 is equivalent to 4C square plus 1203.4C plus 5787.3. So this is a quadratic equation, right? So at the end of the day, when you use your quadratic equation, so you'll be having C equals to 2.8 millimeter. Okay, so as I've said earlier, that okay, if you have your UC beam like this, if you have your UC beam like this, okay, I can easily say that my minimum area, okay, which is as a function of my effective area, because this time around I am not having that zigzag shape, because my base plate, you don't expect my base plate to have zigzag shape. Okay, so I'm not having zigzag shape, definitely. So I'm going to have like a rectangular shape or a square plate, right? So I will just have something like this, but we are using the same concept. Okay, so something like this. Okay, but as I know that okay, from here to here is C, from here to here is C, from here to here is C as always, right? And then from here to here is C. So I can say that my area, which I will call minimum area, my minimum area will now be equivalent to what? So if you want to know what will be the area of this, so definitely from here to here, B plus 2C, and here that will be nothing other than D plus 2C, because you know that the height from here to here is D, right? So C up, C down. Also the length from here to here is B. So you can easily get this area. So I can say that my area, the minimum area, is equal to D plus 2C multiplied by B plus 2C, because if whether this is a rectangle or this is a square, the area is usually length times breadth, right? I believe you understand the difference between the area minimum and the effective area. The effective area is that area in zigzag, okay? But this time around, my area minimum, which is the minimum area, I don't expect to have a zigzag shaped base plate. So I'm going to idealize my base plate to be square or to be rectangle. So that area of that rectangle now is what I'm trying to get, which I am calling minimum area. Okay, and that is as a function of the effective area. Okay, so if you put your D here, you know what D is, you know what C is. C has been calculated already. So my area minimum, which is minimum area, you can easily calculate that to be 43,514 millimeter squared. Okay, so you can see that my area minimum is actually greater than my effective area. My effective area is 9,000. Okay, while this one is 43,000. Okay, 43,000. So what the minimum area simply means is that, okay, when you have your UC beam like this, okay, and your effective area, which is as a function of the C, okay, your effective area is like this total area within the shaded part, effective area, shaded area here is your effective area. Then my minimum area is just this place like this, you know, just idealizing everything. Okay, so that is minimum area. Okay, so minimum area is actually this place that goes inside this void place is no more void anymore, because it has now been added in the minimum area. You understand that now? Area provided now has to be something like this, you know, something like this. Okay, so your area you provide has to be the same thing as your area minimum or more than your area minimum. Okay, so let me see, area that you provide, that is area of this plate that you provide, has to be greater than or equals to area that is minimum. Okay, so if this is my area minimum, you know, I can easily convert this to length and breadth. Okay, so because area is equal to length times breadth, so in order to get that, I can just assume this is like a square plate. Okay, so you say I don't want to keep using red, let me go back to black. So I will say assume square area of base plate. Okay, so that means my length of base plate will be equals to my breadth of base plate, and that can easily be the square root, right, of my area minimum. And what's my area minimum? 43 something. That's 43,000 and everything like that. So now my length will now be equivalent to my breadth, and that will be equivalent to 208.6 millimeter. So I can say 208 by 208.6 millimeter. That is the minimum dimension I can have. So I will just try to, you know, approximate this to, let's say, 250 by 250 or 300 by 300. So I will just approximate this to 300 mm by 300 mm. So this value is the calculated minimum. This is the minimum I can have. This is the minimum I can have if I want to use square plate. But this is the one I have provided. This is what I've provided because I want to provide something at least quite high, that even if the load eventually has been increased, the axial load has been increased from 83 and now increased to 100, this area will still be able to satisfy it. Okay, so that is what I mean by increasing it here. You can't just use the exact value you calculate, which is the minimum. Okay, so from design now, we have easily calculated our area of base plate to be what? 300 by 300. Okay, we have successfully done this one. Okay, so we need to do the other one, which is what? The thickness, right? Because we also need to know how thick the base plate is. So let's go to the thickness part. This video is getting long. I don't want it to be very long, but I think I just need to finish this, so I'll be very fast about the thickness. You know what, let's just meet in the next episode. So episode 4.